Mastering algorithm efficiency in modern software development in today's fast-paced digital landscape, where milliseconds can determine user retention and system scalability. Understanding algorithm efficiency is not just beneficial, it's essential. As developers, we constantly face trade-offs between time complexity, space complexity, and practical performance. This article delves deep into the nuances of algorithmic optimization, exploring both theoretical foundations and real-world applications that help us build faster, more scalable software solutions. Whether you're optimizing legacy code or designing new systems from scratch, these principles will guide your decisions at every level of development. The fundamental concepts of time complexity. Time complexity measures how the runtime of an algorithm increases with input size. It helps predict performance trends without needing actual hardware testing. We express time complexity using big O notation, which provides an upper bound on execution time relative to input growth. This abstraction allows us to compare algorithms objectively across different platforms. Consider three common complexity classes. O(1), constant time operations like array indexing or hash table lookups. O(n), linear time operations such as iterating through arrays or linked lists. O(n) superscript 2, quadratic time operations found in nested loops processing matrices. While O(1) is ideal, choosing between O(n) and O log n often depends on implementation specifics and data characteristics. Real-world factors always influence theoretical predictions. Evaluating space complexity trade-off. Space complexity analyzes memory requirements rather than runtime. Efficient use of memory becomes critical when dealing with large datasets or constrained environments. Optimizing for space might involve techniques like in-place sorting algorithms or compressed data structures. However, these optimizations sometimes come at the cost of increased time complexity. For example, quicksort typically uses less memory than mergesort but may have worst-case scenarios. Understanding these trade-offs requires careful analysis of specific application needs. A good rule of thumb is to prioritize space optimization only when memory constraints outweigh other performance considerations. Most modern systems benefit more from CPU-efficient algorithms than strict memory minimization. Big O notation. Beyond the basics, Big O represents asymptotic behavior, not exact measurements. It tells us how functions grow relative to each other as inputs become very large. Common misconceptions include treating Big O as absolute truth rather than approximation. An O(n) log n algorithm could outperform an O(n) solution for small input sizes due to constant factors. Let's clarify some key points. Constants matter in practice. A 10x slower O(n) algorithm might be better than a 2x slower O(n) log n for moderate input sizes. Best versus worst case. Algorithms like binary search perform differently based on dataset distribution coefficients and lower-order terms. These can significantly affect real-world performance despite being ignored by Big O. Understanding these nuances helps avoid premature optimization while making informed architectural choices. Practical profiling complements theoretical analysis effectively. Practical optimization strategies. Real-world optimization involves combining theory with empirical testing. Profiling tools reveal bottlenecks that aren't obvious through static analysis alone. Some effective strategies include caching frequently accessed data, avoiding unnecessary object creation, and leveraging built-in library functions optimized over years of research. Memory management is crucial too. Using appropriate data structures reduces overhead. For instance, arrays generally offer better cache locality than linked lists. Code refactoring should focus on eliminating redundant computations wherever possible. Even minor improvements compound significantly under high load conditions. Data structure selection for optimal performance. Selecting the right data structure is often more impactful than micro-optimizations. Different structures excel in various scenarios depending on access patterns and mutation frequency. Hash tables provide average O(1) lookup times but require careful handling of collisions and resizing. Trees maintain sorted order with logarithmic insertion/deletion costs. When working with ordered collections, balanced trees, like AVL or red-black trees, ensure predictable performance even during frequent modifications. Choosing between arrays and linked lists depends heavily on expected usage patterns. Arrays favor random access while linked lists handle dynamic sizing more efficiently. Case study: optimizing sorting algorithms. Sorting algorithms illustrate fundamental efficiency principles well. Let's analyze why certain approaches outperform others in specific situations. Bubble sort has poor average performance, O(n) superscript 2, but shines in nearly sorted data. Quick select finds kth smallest elements efficiently but lacks general purpose utility. Merge sort guarantees stable O(n) log n performance but consumes extra memory. Timsort combines merge sort and insertion sort advantages for real-world data. Modern implementations often use hybrid approaches adapting to input characteristics automatically. This shows the importance of context-aware design decisions. Performance considerations in distributed systems. Distributed computing introduces new challenges to traditional algorithm efficiency metrics. Network latency and communication overhead dominate performance profiles. Designing efficient distributed algorithms requires balancing computation against transmission costs. MapReduce frameworks exemplify this principle through data parallelism. Consistency models play a significant role in distributed databases. Strong consistency guarantees increase overhead compared to eventual consistency models. Efficient task scheduling and resource allocation become critical for maintaining throughput across clusters. Load balancing strategies directly impact overall system performance. Profiling tools and benchmarking techniques. Accurate benchmarking requires controlled experiments measuring actual performance under representative workloads. Simple timing tests often miss hidden complexities. Tools like profilers identify hotspots in code, revealing where most execution time is spent. They also detect memory leaks and inefficient memory allocations. Benchmark suites simulate realistic scenarios, helping validate theoretical expectations against real-world results. Comparative benchmarks highlight differences between competing approaches. Automated testing frameworks enable continuous monitoring of performance regressions. This ensures optimizations don't introduce unintended side effects over time. Emerging trends in algorithm optimization. Quantum computing promises radical changes in algorithm efficiency, enabling exponential speedups for specific problems. Shor's algorithm demonstrates this potential clearly. Machine learning is increasingly used to optimize algorithms themselves. Reinforcement learning agents can discover novel optimization paths previously unknown to humans. Hardware advancements continue influencing algorithm design. GPUs and TPUs demand specialized algorithms taking advantage of massive parallelism capabilities. These developments suggest future algorithms will need to be adaptable, self-tuning, and capable of exploiting diverse computational architectures effectively. Conclusion: algorithm efficiency remains central to building high-performance software solutions. Balancing theoretical analysis with practical implementation yields optimal results. Continuous learning and experimentation are vital for staying current with evolving technologies. By mastering these fundamentals, developers empower themselves to create robust, efficient systems that scale gracefully with growing demands.